This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
This is Robert for Software Engineering Radio. I'm joined by Eric Lubow. Eric is the CTO of SimpleReach, a social event publishing platform. Prior to SimpleReach, Eric worked at Guardian Digital, Conductor.com, and Sherman's Travel, where he built an email system with analytics to send over 100 million emails per month. Recently, Eric has presented at Cassandra World Summit, the New York City CTO School, and at Interop New York. Eric, welcome to Software Engineering Radio.
Hi, Robert. Thanks for having me.
You're welcome, Eric. Today, Eric and I will be talking about polyglot persistence. Eric, I have built database applications before. It's pretty straightforward. You pick a database, either MySQL, Oracle, or SQL Server, and you choose an object relational mapping tool for whatever platform you're on, and then you write your app, and that's all there is to it, right?
Theoretically, yeah. I mean, when you're building a small application, you definitely have to go with what works. You definitely should start with what you know. When we started out at SimpleReach, we were a group of folks who thought Mongo would be useful because it was built for larger, it was made to scale, and we thought that we'd be able to use what we knew with Rails. And the first iteration of what we built, we thought would work like that, and it did. It worked pretty well. But it's one of those things that you start with what you know, and then when you realize what you know may not be sufficient to handle the scale that you've gotten to, which, by the way, is a luxury problem, then you adjust accordingly.
Would you agree that it's no longer a given that an application will have a single data store?
No, actually, I don't. I don't think that it's a given at all. It really just depends on what your application is and what it's used for and what your scale is going to be and what your usage patterns are. And as a result, you could have a single data store and you might be able to do everything you need to do with MySQL and or Postgres and the internal caching engines. I mean, those work just fine. So it really just depends on what your application's for. But if you need something that's going to perform at scale, like I would be incredibly surprised if you could do it with a single data store.
Eric, then, in your opinion, is scale the primary thing that's pushing applications to use multiple data stores?
I think it's usage patterns, different usage patterns within an application. Certain data stores are made to service different usage patterns better. For instance, one of the best things about Redis is that you can guarantee that everything is memory mapped all the time because that's the way it works. But with Mongo or Cassandra or even MySQL, the only things that are going to be memory mapped are the things that have been most recently used and are still in the cache, which could present a bit of a problem if you need something quickly and you're not sure whether or not it's going to be back in a few milliseconds or a few hundred milliseconds, and that could always affect the user experience. Whereas with Redis, you may not be able to have the same query patterns, or Memcache for that matter, you may not be able to have the same query patterns, but you can pretty much guarantee that whatever you're asking for is going to come back fairly quickly.
I think, though, that even with a single data store, and let's say it's MySQL, that if your application's small enough, then everything will be served out of memory. So isn't it really some combination of scale or latency that is pushing the application away from a single data store to multiple specialized stores?
Yeah, it still is ultimately scale and usage. Obviously, there's no point in putting a huge Redis server in front of something that's got about 10 or 15 users, because MySQL will be able to handle all of that. But it also depends. Maybe those 10 or 15 users are storing, gigs of data per session, and you don't want to have to ask MySQL to hold on to that in its query cache or its key cache, especially if you're slicing and dicing those gigs of data quite heavily. So maybe you want to put, pre-computed queries into Redis, and you have some intermediary engine say, hey, let me check the cache first before I go down to the database.
So I think the theme you're getting at there is choosing the right tool for the job, and that maybe gives you a different answer for different features of your application.
100%. I mean, that's I actually when I give these presentations, these talks, I always end up there's a few slides that I invariably include every time. Some are for entertainment value, but they also convey the idea of, so for those people who know what home improvement is, the show with, Tim the Toolman Taylor, he's always got the right tool for the job. And I got a picture of him standing there saying the right tool for the job, because that's basically what you're after. There are a lot of tools out there, and you need to know what your job is and what the best one to use is. And, what the job is typically about data size, data access, data storage, data consistency. And those are the questions. Those are just a few of the questions on the data side. I mean, there's, anywhere from 50 to 50, there's 50 plus questions you have to ask when you're starting to build something out that becomes much larger than your prototype or your MVP.
Eric, I'm not going to ask you to list 50 things, but could you pick top 5 questions that you'd be asking when you're trying to make those decisions?
Sure. When you are looking at, so I tend to put these things in a few different categories. I basically set it up as data, technology, financial, and other. And if you got those other questions, those are typically things like, do I have any legal requirements? Like HIPAA, FIPS, Sarbanes-Oxley, PII requirements, things like that. Support if you need it. Is there a community around it? The data questions are talking about your query patterns, your data ingestion volume, loading and unloading of data, backup style, what are your display requirements? The technology side may be more infrastructure related. Do things need to be encrypted or compressed on the file system? What level of fault tolerance do you need? Is there support for monitoring in your language, the language that you and your team are most comfortable developing in? I mean, then there's other just general financial questions like, is this going to require a lot of hardware? Do I need to come up with a cloud or an iron hybrid? Do I need to be all in the data center as a result? What if something goes wrong? What do I do? Is it going to cost me for support? Am I going to be able to do this with a community? I mean, there's tons of questions in those categories that you're going to have to ask yourself and your team to make those decisions. Those are just sort of the superficial ones that need to, that we found most important to address. But there's certainly a lot more that I have listed and have asked.
Sure. So you mentioned the programming language. Would you say that you start from programming language that your team is comfortable with, and then you look for persistent stores that have good drivers in that language? Or are you generally, are the data requirements so much of a constraint that you need to pick a data store and then maybe learn a new language to access that data store effectively? So
that's a great question, because it's actually something that we faced at Simple Reach, and we had to make that decision. So we went through and we knew that there were certain requirements we needed to make, and the two that sort of fell into what we were most interested in was HBase and Cassandra. And for reasons that I can get into if everyone would like, we ended up at Cassandra. And what we ran into was that a fair portion of our stack was Ruby and Node. Well, the Ruby driver was really just a wrapped Java driver at the time. And the Node driver was pretty tough to work with. So what we ended up doing was, once we figured out that Cassandra was the data store that we needed to make use of, we started shifting parts of our stack over into Python, because their Python driver, PyCasa, is excellent, very well written, and very performant. And the Node driver, we knew we needed to access the data store in Node.js. We ended up having to roll our own Node driver, which is actually now turned out to be the standard in market, because we just happened to, and I say we, meaning the organization, but I tell you, I did not have much to do with the writing of it. We did a great job of writing it, and we've gotten a lot of help from the community to make it better. So there was a little bit of having to roll our own and reinventing the wheel. It was certainly the last resort, but it was done and it was necessary for us.
That means that I should have given you 3 options rather than choose the language that has a driver or choose the data store. The third option is write your own driver.
Yeah, we were not thrilled about having to do that, but once we found that the access patterns that we needed to take advantage of weren't available in the Node.js driver that Twitter had written, or the one that was hosted on Google Code, which I'm not quite sure who wrote, we found that, well, this is one of those few options where you kind of have to do it yourself.
Okay. Well, Eric, you said data as is your number one question when I asked you about the differentiating factors. Could you drill down into that a little bit and talk about what are some different access patterns, and when you see a certain access pattern, what kind of data storage solution would that point you towards?
Sure. So it's actually not as clear cut as that. Although when I was first getting into these questions, that's really what I thought it was about, was just the query patterns. But it actually turns out to be quite a bit more than that. All right. So when we first started asking questions about what the proper usage patterns were, we thought that it really came down to query patterns. And the fact is that that's important, but it's not the end-all be-all. And we drilled it down into a couple of subcategories. And one of them is certainly, what are my query patterns? Am I going to be pulling in slices of data? And a slice of data may look like, if in Cassandra, if a row is everything that happened for this hour for a particular URL, that means that I've got all the page views, all the tweets, all the Facebook actions, et cetera, et cetera. So can I slice out all those Facebook actions and then look at them individually? That would be a query pattern. And you can do that in various data stores, but Cassandra happens to be very well suited to just slicing out anything that starts with the word Facebook. And if you have it in composite columns, then it's good there. Another thing that's very interesting, for a very interesting question to ask, is what is your data input methodology? Are you batch loading? Are you taking data in at a high volume, high velocity? Does the data need to be aggregated as it's coming in? Does the data need to be immediately available everywhere on its way in? So all these are questions around ingestion and just basic input stuff. So, you can answer those with, am I under the eventual consistency requirement? Am I required to have real-time data immediately available? And what are my ingestion points? Can I write data anywhere? With Cassandra, you can write it anywhere. The eventually consistent thing makes it show up immediately, or makes it show up not necessarily immediately, but within typically a pretty reasonable amount of time. And because you are writing to many servers, you don't have to worry about overloading one server, unless you have a hotspot, in which case you may need to think about redesigning your schema. Another big question that you need to look at is, what are your display requirements? Does the display pattern require you to pull data out immediately? What does the query look like for those displays? Is it aggregated? Is it raw? All those things lend itself to determining the design pattern, both for input, storage, and analysis, or for all three of those things. So that, once you can answer the question of what your display requirements are going to look like in some shape or form, you can start to narrow down which data stores will work well for you. So there's actually a lot of questions that go into this. Again, I'm sort of scratching the surface, but as you build that first version of an application, and Mongo is great for building a first version of an application because it's NoSQL, you can just build and iterate and iterate and iterate, and as you start to see things develop, you can say, you know what, Mongo is going to be absolutely fantastic for what I'm doing. I don't need to change anything. Or you can end up where we were and say, hey, you know what, Mongo is really great for a portion of our system, but it's not going to be able to hold up for everything we do. We need to explore other opportunities or other options. And that's what we did. And that's how we ended up in the polyglot persistence realm.
So Eric, are you recommending then to application architects start with something that's general purpose that will meet as many of your needs that you can anticipate in the immediate future, and then gradually swap out different pieces of the system when your initial solution breaks?
Yes, that's actually exactly what I'm saying. Because if you get to the point where your solution is breaking, it means that you've either done something horribly, horribly wrong, which we've certainly done ourselves, or it means that you're growing. And, growth and scale are luxury problems, but they are problems nonetheless. So over-architecting and over-engineering is something that we as engineers love to do. We're like, oh, new toy, shiny object, let's play with this. It's either, not something yet, or it's may not be what you need. So you got to start with something start with a very good multi-purpose tool, get as many ideas out of your head and into the application as you're willing to build for your MVP, and see what breaks. If things start to slow down or need fixing, that's when you may need to explore other options.
So Eric, I recall one situation where I was trying to sell a manager on the idea that they needed a specialized type of data store for certain aspects of the system. And the answer I was getting was, yes, but then we would have two databases. And that was stated like that was the killer argument, and I should just drop dead. Do you think there is a bit of a cultural change that organizations need to make if they have been building systems and there is a ironclad rule in your mind that you have one data store?
So there's a few things that I think need to be addressed in that question. Absolutely, I do agree that there is a culture change that's required. But something that you have to keep in mind is that the idea of having a lot of data, what the term big data or having a lot of data means, has drastically changed over the past 5 years. With Amazon Web Services and hardware getting cheaper, and compute power getting cheaper and more widely available, the amount that people can do with, or what people can do with a large amount of data, is becoming more and more and more. So, whereas maybe a couple of years ago, maybe 10 years ago, if you wanted to do something interesting with the census data, like, odds are you wouldn't be able to store that on your hard drive. Now, you may or may not be able to store that on your hard drive, but you could certainly grab an instance in the cloud and have a few terabytes across an EBS set of EBS volumes, store that, and run some interesting analyses on it.
Yeah, so and in a year from now, we'll be able to store it on your mobile phone.
Exactly. I mean, there is a definitive change in the availability of both storage and compute power that allows for these things. So that in and of itself is a huge culture change. So people who are not willing to step in with that culture change are certainly not going to be willing to explore a new idea of perhaps having multiple data stores. Now, the other reason, in my opinion, that I've seen this hesitation around multiple data stores is that There's certainly a requirement. There's a knowledge requirement around it. I mean, if we have 4 data stores at Simple Reach, that means that at least one person has to know how to work each of those 4 data stores. Like, if there's 4 people, then one of them has to be an expert in some way, shape, or form in each one of them. Because when something goes wrong, somebody has to know how to fix it. So at that point, you're already your requirements for personnel goes up, your requirements for knowledge go up, and it's not that engineers aren't up to the task or willing, but it's more. There's a lot more that has to go into it because again, there's only so many hours in the day, and then you're managing more data stores, you're managing more people, you're managing more machines, and more applications within that. So when you have multiple data stores and you have potentially your data stored across multiple data stores. A natural thing when most people who come from RDBMSs will say, well, if I have one thing in one data store and one thing in the other, why don't I join them? Well, that's a dangerous thing to do because now your intra data store or inter data store joins are very slow and they're cumbersome and you have to figure out new ways to access your data, which means new paradigms within applications. So you're essentially looking for a culture change in institutional knowledge. You're looking for a culture change in availability of data and applications. You're looking for a culture change in usage patterns. And all these things are very scary to a manager who's got a budget.
Sure. So you're going into something, Eric, that I find really interesting, which is from a system architecture perspective, how do you know when you've got the right overall balance of optimality for each feature versus managing the complexity and the cost of the entire project? And if each developer or each team is looking at what is optimal for their problem, they might arrive at a particular data store that's ideal for what they're doing. But how does, from a project perspective, you make this trade-off between the growth and complexity and cost of the entire system against doing something better, or maybe just living with the fact that you're going to do something not as well?
Yeah, that's tough. It's certainly tough in larger organizations who may not be as flexible. One of the beautiful things about being in a startup is that if something's not working, you have the option, generally speaking, to ditch it and try something else. So it's really hard to gauge, from the big company perspective, when it's okay to ditch something and try again, how much legacy you have to support. Because in a startup, typically you're not going to be supporting a whole lot of legacy problems or legacy data stores or applications. So it's a very different set of requirements typically that you're entering into this decision with in a smaller organization than with a larger organization. But they're all things that you have to keep in mind.
Sure. I remember seeing a talk by somebody who was explaining why they decided to build a messaging system on MySQL so they could take a custom messaging system out of production because they wanted to reduce the load on their ops guys from having to manage additional pieces of middleware. And they felt like that was the right decision for them to have one less infrastructure piece rather than one more.
Yeah, to me that just sounds scary, to be quite frank, because you're re-architecting something that you're reinventing the wheel when odds are there's something that's already there to do a job, to do that particular job. I mean, the amount of messaging systems that are out there that use more high performance systems than MySQL, there's a ton of them. ActiveMQ, RabbitMQ, Bitly just built their own NSQ, and Bitly has done a phenomenal job of releasing tools and building their own tools in-house, which is typically something that you don't see done a lot. But between like NSQ and Doubloons, like Bitly's done an excellent job. So while that's generally a scary thought to re-architect, it's sometimes can be useful.
Yeah.
that sort of gets into the build versus buy argument.
Sure.
Where buy, I guess, in this term is, use open source available tools, but does typically get into the build versus buy.
Yeah. Now, I would like to delve a little bit into another big architectural pattern that's going to come up when you're building this type of system. Do you recommend that applications code directly against the driver for each data store, or would you put an abstraction layer around, let's say, real-time analytics, aggregates, whatever your core abstractions are, and then give yourself the ability to swap in or swap out different persistent stores based on without then having to re-architect or recode your applications?
Sure. So again, I'll address this through the lens of Simple Reach because of what we did. What we ended up doing was we built a service architecture. So anything that does any reading of data whatsoever, it hits our internal API. And our internal API is essentially a service architecture. It speaks JSON because every language has, JSON bindings in some way, shape, or form. They're all pretty fast. And any read query, it just hits the API. And the API says, you know what? I know which data store I need to get this data from. I know how to make it look. The internal architecture is written in, the internal service architecture is written in Node.js. So if it needs to go out to multiple data stores at the same time, you can fire off a bunch of threads, hit Cassandra, hit Redis, and hit Mongo, and come back, aggregate the response, and then one single JSON response back to the requester or whatever the requesting agent is. What we found, though, is that does not typically apply as well for writes. It does slow down writes quite heavily, so we actually haven't solved that problem yet. So we tend to write things directly to the data store, not going through that service architecture. But for reads, it has made a huge dent in solving the speed problems that comes with having this multiple data stores. So the architecture itself, having the internal service architecture, lends itself very well to being able to plug and play. A great example of what this did for us is when we were trying to find the proper analytics package to help us get off the ground, and we were trying to decide between infobread and InfiniDB. They're both MySQL storage column storage engines. So they both work with the MySQL driver. They both speak MySQL. So what we did was we put both of them, we spun up one machine for each, one for infobread, one for InfiniDB, and then every request that was supposed to go there went to both machines simultaneously. They were both timed, and for consistency's sake, you always want to read from one machine. So in case the data gets a little bit out of sync, the client doesn't end up seeing some weirdness. But we sent both queries to both. We used all of our responses were from InfiniDB. Then we take a hashed version of the query, store that in Mongo along with the response times, and we just built up this huge response time database, a collection rather, in Mongo of the query and how long it took to respond, the query and how long it took to respond. We took a look at the graphs and we found that certain queries perform much faster, certain query on one type, certain queries perform much slower. We ended up making our decision. We went with infobread for a variety of reasons. We ripped InfiniDB out, and there was absolutely no downtime because all we had to do was just say to the service architecture, from now on, go with the infobread responses. And there it was.
That's a great story, Eric. Probably better to been able to do that on the live system in production than trying to set up on a test network and benchmark them against test data.
Yeah, that was part of it. And then once we realized that, hey, we can't just have one server, because anybody who's ever built a fault-tolerant system knows that a single point of failure is always the point that's going to fail. We added a second machine, so now we have two identical InfoBright machines, and they both load the data simultaneously. And we just built into the service architecture. If you go to the primary InfoBright machine and it stops responding, go ask the other one. When we needed to add the second InfoBright machine for redundancy, we just set it up so that both InfoBright machines would continue to load all the data regularly, and with no downtime whatsoever, we added the second machine in, and the rolling restart across the service architecture, the internal API, allowed us to just say any query that comes in, go immediately to the first InfoBright server, and if that's down, go ask the other one.
So I'd like to shift a little bit to another topic. Something I've seen can be very disruptive in these systems with multiple data stores and multiple programming languages is, I guess I would call it schema evolution or data model evolution. Now, instead of your data tables and your objects, you've got times n. How do you manage that process how do you manage that process efficiently?
Are you talking about just determining what the best schema is for the data, or?
No, you've got version 1 of your application, requirements change, or you build a new feature, now you have to modify the schema, but it's not just in one place, it's in 5 places, and it's in 3 different programming libraries.
Right, so that's what's good and bad about that service architecture, because the read pattern never has to change. The only thing that needs to know about that read pattern is the service architecture. Anything that's requesting the data just says, yep, just continue giving me the data, and then you build a map inside of that service architecture to say, this is what it looks like now, this is what it used to look like for this request. So, theoretically, you could hit a point in which those maps become a pain in the butt to deal with. There's too many of them. We haven't hit that point yet, knock on wood, but it's certainly plausible for that to happen. On the right side, on the other hand, we actually haven't run into that yet. We've come across a couple of different ways that we've had to read the data, but in terms of writing the data, the only thing that we've had to do is write it in additional formats. We haven't had to redo one of the formats that we're writing with.
So that hasn't really been that much of a big deal for you at SimpleReach.
Correct. Excuse me. The reason that we've had to redo some of the way we write the data, add some of the ways we write the data, is because the features that we're developing have different display requirements. So it's faster to query data that looks like X than looks like Y for a certain feature. So because storage is cheap, it's just easier for us to write the data and make it look a different way. So we may have the data stored 4 times, this piece of data stored 4 times, now we store it a 5th time. But it makes this feature that we're developing much faster to develop and very easy to use and implement, so it's worth it.
I would think in this type of architecture that it puts even more importance on overall system testing, because everyone could test their own little piece of code that writes to one data store, but that doesn't mean that the entire system will behave correctly, because you have greater possibility of consistency problems. Is there anything to that?
Yes. Consistency across data stores is a huge problem for us, or was a huge problem for us, rather. And, the way we solved it was we have our front-end application, and then we have an entirely separate back-end application, an admin section, so to speak. And when this management or admin section is used most frequently, or where it's used most frequently, is We have built many screens that look across the data stores at certain types of data and say, does this look the same in each of the data stores where it's supposed to look the same? So we have programmatic checks, and then we have visual checks in case we're unsure about the programmatic checks. That was a lesson that we learned the hard way by seeing, in one data store, this thing has 10 tweets, and in another data store, this thing has 14. And we're like, okay, what happened there? And in order to figure that out, we started building programmatic checks. And we're like, okay, programmatically, it looks like it should have worked. What happened? Then we go and make the visual checks, and we're like, oh, okay. So we started building screens in our management section to compare data stores and responses from the service architecture to make sure that we were getting back what we thought we were getting back, and to make sure we were writing what we thought we were writing.
Did you find it difficult to track down where things were going wrong?
At first, there was difficulty because we were sort of fudging our way through the process. That's a bit of a logic issue in a lot of cases. But as we got more adept at, the patterns of moving data around from one engine to the other, sort of realized that there's a good way to do this and a bad way to do this. And it's a set of best practices that really didn't exist. We were sort of fudging ETL processes, and we figured out that, one, we should be documenting how we do this so that when somebody else comes along and tries to do something similar, they're fudging their way through and trying to figure out best practices as well. And as much as it's unpleasant sometimes to test and write tests when you're trying to iterate quickly in a startup, in this sort of situation, it's useful.
Is your system structured in such a way that all of your business critical data has a single master copy somewhere, and if you lost all your data stores but one, you could regenerate everything from master? Or do you have multiple distributed master copies of different pieces of data depending on where that data lives?
Again, great question. This was something that we didn't really consider up front, but we came along after a while and said, you know what? There has to be an authoritative data source. So everything needs to be able to be rebuilt from this. And we decided that was Cassandra. So everything that we do first gets put into Cassandra and then gets shifted elsewhere. There might be other simultaneous things going on, like as we write a raw event to Cassandra, we may do a couple of increments in Mongo and some sets or increments in Redis as well. But there's always going to be an action in Cassandra. So that means that not only is that distributed and not only is that fault tolerant, but it's also the one and only place that we have everything. And the reason that we chose that is because we have nodes across many availability zones. So if Amazon were to lose all of US East 1A, we'll still have a couple of copies of our data in 1B and 1E and 1C. And if Amazon were to lose 1A and 1E, we still have 1B and 1C. So we can regenerate the machines we can regenerate the data on the other data stores from those machines. Now, that being said, we have our entire architecture spread out across availability zones. So, we have Mongo has the concept of replica sets and shards. So every shard that we have has at least 2 replicas in 2 availability zones. For MySQL, we have 1 in 1 availability zone and our secondary in another availability zone. So if Amazon took a really, really nasty hit and lost 2 availability zones, well, then we would have a problem, as well as a whole lot of other people. So that's not really an eventuality that we're concerned about, but we've done what we can to protect ourselves against data loss in that respect.
To what extent then was the choice of which technology would serve as a master driven by the way that Datastore handled the multi-data center distribution?
Almost entirely, actually. When we were coming to the conclusion, when we were coming to the consensus internally, what really would be an acceptable authoritative data source, we really said, okay, there's two things that this authoritative store needs to be able to do. One, be distributed. It has to be distributed and be able to survive, partial failures, outages, node losses, whatever it is. And in our case, what we consider to be that partial outage would be losing an entire data center. I'm sorry, losing an entire availability zone. The other part of it was because whatever is going to be authoritative is going to have a high volume of data ingestion and a high velocity of data ingestion, it needs to be able to handle all that and then distribute it without slowing anything down. So, right now, as we're still in our growing stages, we're looking at a few 100 million events per day, social events per day. We're looking at over a few million URLs. And that translates to, a couple thousand of events per second. We have to ingest, store, and manage. So all that meant that, we had to figure out what would be the most fault tolerant and be able to store all the data coming in at a high velocity and a high volume and wouldn't slow down any of the read patterns. So, we looked at Mongo and said, hey, Mongo is working well for us, but it's not been our experience that we can do all these writes to it and not slow down the reads. So what we ended up doing was saying, okay, if we look at what Cassandra does and how it does it, we can do high volume, high velocity ingestion, and we can write to any node, and we can lose those nodes fairly quickly and still have that data elsewhere. It's actually, for us, came down to not only the fault tolerance and the distributed nature, but also the ability to hold on to and ingest data very quickly.
And that you have some kind of piece of your system where you could, starting from your master copy, repopulate everything else from zero if necessary.
Yes, it would be extremely arduous, very tedious, and it would take a while. And writing those MapReduce jobs would not be very pleasant, but it could certainly be done if it needed to be done.
So you mentioned earlier, I want to come back to the notion that big data, the idea of what that means, has changed a lot in recent years. Where do these so-called big data technologies like Hadoop and HDFS and the other platforms built on top of that, where do they fit in to the picture?
Well, there was a very interesting question that was posed when I was at the New York City CTO meetup, and somebody said, well, what does big data mean to you? And do you like, to me, I'm not a huge fan of the term big data in general, because big is a very subjective term. What's big data to Simple Reach is clearly not big data to Google, or Facebook. So if we both classify ourselves as big data companies, in essence, we both do, the meaning becomes slightly skewed. So to me, being a data company in general means that you're working with a significant amount of data. Now, again, significant could mean whatever it is to you. Maybe it's the size of a spreadsheet, something just slightly bigger than will fit in an Excel spreadsheet, or maybe it's something else. Maybe it's something once you hit 1 terabyte, maybe it's once you hit 100 terabytes, or once you hit a petabyte. It's got different meanings to different people. So when you look at the evolution of these products and their distribution, a few years ago, most companies couldn't use these, as I said earlier, because there was no way to deploy these without a fair amount of money. Being able to store 10, 15 terabytes of data, required a fairly sizable investment. And that was not common. There was not a whole lot of data center knowledge to support that in a distributed through the masses like there is now. So as these tools started growing, the compute power and the storage, as the compute power became more available and the storage became cheaper, then people started getting into these these engines like Hadoop and like all the MapReduce frameworks, and there are all these other companies now that are coming up around it. Like DataStax is doing a lot with Cassandra and being able to run Hadoop on CFS using Hive and Pig and things like that. And there's even Google is sort of publishing their papers and helping along technologies like Dremel, I believe it's called, which is their rolling SQL query like engine, which is now being picked up by the Apache Foundation. So all these things that are coming down the pipe are just making the processing of data more available to the end user, and in this case, the end user is typically businesses and organizations who are coming up through the ranks.
Eric, earlier you talked about a big decision you made between HBase and Cassandra. Could you walk us through how that process went?
That we needed to take advantage of some sort of MapReduce technology because we knew that the way our data was going to be stored and the amount of data that we were going to be looking at was going to require this. But we didn't really know what the right direction was. So we started taking a look at HBase. We started looking at Cassandra, and we looked at a couple of others, including Riak, and there's a ton out there. We looked at DynamoDB and EMR. Elastic MapReduce, and we really came down to a few things. First, we pretty quickly ruled out Riak at the time because it was just the tools were just a little too immature. I don't believe that's the case anymore, but at the time we were looking, that was the case. We also pretty quickly ruled out using DynamoDB on Amazon and Google App Engine, because the problem that we saw was that you could very easily code yourself into a corner. If all of a sudden you need to start doing things with your database, so if all of a sudden you start needing to do things with your data that's not under the basic storage and query patterns of App Engine or DynamoDB, then you have to wait until Amazon or Google comes out with a new release and hope that what they're releasing will help you with what you're doing. And if not, then you have to figure out a way to get all of your data out. And if you have terabytes of data, that could be, a very problematic endeavor. So that sort of left us with HBase and Cassandra. And when we looked, we did talk to Cloudera about HBase, and we talked to DataStax about Cassandra. And, there were a bunch of factors that we were considering, but the biggest one that led us down the road of Cassandra was the fact that we had an influence in the roadmap. At the time, and again, Cloudera has done a great job since then of changing this. At the time, the roadmap for Hadoop as it related to HBase was very nebulous. There wasn't a clear, these are the people who are in charge, and these are the people who are pushing HBase in the development forward. And Cloudera was trying to get their foot in there, and since then have done a fantastic job of really pushing HBase forward. But at the time, it just wasn't there. And speaking to the folks at DataStax and being able to become a part of the community and as integral a part of the community and drive the roadmap in the way we have, and it's not just us; they do it for everyone. Which is another great thing about them. That really gave us the comfort level with our decision, and being able to talk to people consistently about the roadmap and perhaps injecting what our use cases are and how the features could be helpful to our use case, because odds are we're not going to be the only one with a particular use case. We just might be the ones who are most vocal about it at the time. So ultimately, the deciding factor was, hey, we can do pretty much the same thing with HBase as we could do with Cassandra, but having somebody be attentive to the roadmap needs and where we were heading was probably the deciding factor for the major deciding factor for us.
Eric, if people would like to learn more about you and follow your ideas, how can they do that?
There's a couple of ways to follow me. First, I have a blog, which I don't keep updated as regularly as I'd like to. but I have a couple of posts in the pipeline for the next few weeks at eric.lubow.org. You can also follow me on Twitter at elubow, ELUBOW. Those are probably the easiest things to do. I also do speaking engagements here and there. I will be speaking at Mongo Boston on October 24th if you're in the Boston area.
Great. And if listeners would like to learn about Simple Reach, how can they do that?
Yeah, generally Simple Reach gives content creators the ability to see how well their content does socially. So if you create content, if you publish articles or videos or anything along those lines, we can help you. So if you head on over to www.simplereach.com and sign up for our public beta, which is where we're at the moment, we can certainly help you see how well how your content's doing.
Eric, thank you very much for speaking to Software Engineering Radio.
Thank you very much for having me, Robert.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To support us, you can advertise SE Radio by clicking the Dig, Reddit, Delicious, or Slashdot buttons on the site, or by talking about us on Facebook, Twitter, or your own blog. If you have feedback specific to an episode, please use the commenting feature on the site so that other listeners can respond to your comments as well. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Please see the website for details. Thanks again for your support.